The authors propose an aspect-oriented method, AoM, for multimodal aspect-based sentiment analysis, MABSA, which aims to extract aspects from text-image pairs and recognize their sentiments. This method addresses the limitations of existing methods by detecting aspect-relevant semantic and sentiment information using an aspect-aware attention module. AoM selects textual tokens and image blocks semantically related to the aspects, reducing noise and improving aspect-based sentiment analysis. The method also explicitly introduces sentiment embedding and uses a graph convolutional network to model vision text and text-text interactions. The authors highlight the importance of accurately aggregating sentiment information and demonstrate the superiority of AoM over existing methods through experimental validation. Aspect-oriented method, AoM, is proposed to mitigate textual noise from confusion among different aspects in image-text interactions. AoM consists of two key modules: Aspect-Aware Attention Module, A3M, and Aspect-Guided Graph Convolutional Network, AGGCN. A3M semantically aligns image and text by computing aspect-relevant token representations based on their relevance to aspect features, effectively detecting aspect-relevant multimodal contents from a semantic perspective. AGGCN aggregates sentiment information by constructing a multimodal weighted association matrix containing aspect-to-image block similarity and word-to-word dependency, and then applying a graph convolutional network. This approach enables the detection of aspect-relevant multimodal contents from a sentiment perspective. The combination of A3M and AGGCN enables AoM to mitigate visual and textual noises from complex image-text interactions. Existing methods for aspect-based sentiment analysis, MABSA, leverage pre-trained language models like BERT and graph convolutional networks or graph attention networks to model dependency relationships between aspects and their descriptions. Multimodal aspect-based sentiment analysis, MABSA, methods utilize images to supplement aspect term extraction and sentiment analysis, and can be divided into multimodal aspect term extraction, MATE, and multimodal aspect-oriented sentiment classification, MASC, subtasks. However, previous MABSA methods neglect fine-grained visual block alignment with corresponding aspects, introducing irrelevant visual noise, and ignore modeling syntax dependency and sentiment information for aspect descriptions. AoM addresses these limitations by incorporating A3M and AGGCN, which respectively address semantic alignment and sentiment information aggregation. Experimental results on Twitter 2015 and Twitter 2017 datasets demonstrate that AoM outperforms state-of-the-art methods, highlighting its effectiveness in mitigating textual noise and detecting aspect-relevant multimodal contents. The research methodology focuses on the aspect-oriented model AoM, capturing semantic information through fine-grained image-text alignment and aggregating aspect-relevant sentiment information. This is achieved via an encoder-decoder architecture based on BART, incorporating the aspect-aware attention module, A3M, and aspect-guided graph convolutional network, AGGCN, to align textual aspects with their visual and textual descriptions. The feature extractor utilizes pre-trained BART for textual representation and ResNet for visual blocks, ultimately producing an output that represents all aspects and their associated sentiment polarities. The aspect-aware multimodal alignment, A3M, module is designed to align visual and textual modalities, leveraging candidate aspects extracted using the NLP tool spaCy. These candidate aspects features, denoted as HCA, are obtained from the hidden state of the BART encoder. An attention-based mechanism is implemented to capture the relationship between candidate aspects and atomic features, guided by the candidate aspects. The attention distribution alpha T over K candidate aspects is computed using equations 1 and 2, where ZT is the comprehensive feature extracted from both the candidate aspects and the hidden states. The aspect-related hidden feature HA_T is then calculated as a weighted sum of all candidate aspects, as shown in equation 3. To combine the atomic feature HT and its aspect-related hidden feature HA_T, a learned parameter beta T is introduced to add up the two features, as shown in equations 4 and 5. The final output of A3M, denoted as HT, is the noiseless and aligned information for every atomic feature. A pre-training task is also described to align the two modalities and reduce noise. Specifically, the image-text relationship on the TRC dataset is detected using the output of A3M and a fully connected softmax layer, with cross-entropy loss as the training objective. Furthermore, the authors introduce the Aspect-Guided Graph Convolutional Network (AGGCN) module to mitigate sentiment interference among different aspects. AGGCN incorporates external sentiment information from SenticNet and projects it to the same dimension as the aspect-related hidden feature HA_T. The sentiment feature C is added to the output of A3M, resulting in the feature HS_I with effective knowledge. A Boolean dependency matrix D is constructed among visual blocks and words, where the word-to-word part is represented by submatrix DTT. The AGGCN model is a multimodal sentiment analysis framework that integrates textual and visual cues to identify aspects and their corresponding sentiments in images and texts. By leveraging a pre-trained BART model for encoding input text and image, and a graph convolutional network, GCN, to model complex relationships between words in the sentence and aspects in the image, the model captures nuanced sentiment information. The input text is first processed by the BART model to generate contextualized representations, which are then combined with image features extracted from a pre-trained ResNet model. These combined features form the initial node representations for the GCN. The association matrix A, calculated based on textual and visual dependencies, represents the strength of association between two nodes in the graph. Through multiple layers, the AGGCN updates node representations by aggregating information from neighboring nodes and refining sentiment information. The final output, HS, captures sentiment information for each aspect. The BART decoder takes this output, along with previous decoder outputs, to predict token probabilities for the next word in the sentence. The model's loss function is defined as the negative log likelihood of the target sentence given the input. Trained on Twitter 2015 and Twitter 2017 benchmark datasets, with hyperparameters lambda1 and lambda2 set to 1 and 0.5 respectively, the AGGCN model outperforms state-of-the-art baselines in both datasets, demonstrating its effectiveness in multimodal sentiment analysis tasks. The comparison of the proposed aspect-oriented multimodal fusion (AoM) model with state-of-the-art models in multi-aspect-based sentiment analysis (MABSA), multi-aspect target extraction (MATE), and multi-aspect sentiment classification (MASC) tasks highlights AoM's effectiveness. In MABSA, AoM outperforms all models, demonstrating the value of learning aspect-relevant visual blocks and textual words. For MATE, AoM achieves the best F1 score on Twitter 2015, with a 0.3% improvement over the second-best model, CMMT. The paper discusses various baseline models, including SPAN, DGCN, BART, and others, providing a comprehensive overview of the current landscape in multimodal sentiment analysis and target extraction. The paper explores the performance of various methods for sentiment analysis on Twitter datasets, with a focus on MATE and MASC. It introduces the aspect-aware model, AoM, which surpasses existing methods by utilizing multimodal information and aspect-specific modules. An ablation study underscores the significance of each component in AoM, illustrating the efficacy of the aspect-aware attention module and aspect-guided graph convolutional network. A case study provides examples of how these modules enhance sentiment analysis accuracy by concentrating on specific aspects related to blocks and words. The A3M model's multimodal sentiment analysis focuses on relevant aspects, with attention weights indicating Mayer Kadokawa as the most relevant. The AGGCN module incorporates word-to-word and word-to-visual block association matrices, excluding sentiment interference by utilizing syntax dependency information. Figure 6 visualizes attention maps, demonstrating the A3M's ability to detect aspect-relevant information, focusing on Mayer Kadokawa and Kyoto, with distinct attention patterns. This highlights the significance of aspect-oriented attention in improving sentiment analysis accuracy. The research paper presents a novel approach for aspect-based sentiment analysis in multimodal data, integrating both semantic and sentiment information. It proposes a two-stage process. First, extracting aspect sentiment pairs from the data, and then classifying these pairs into positive, negative, or neutral categories. The authors introduce an innovative aspect-oriented multimodal network, AoM, model, combining visual and textual information through a dual-graph convolutional network. This model effectively captures relationships between aspects and their sentiments in multimodal data. In the first stage, a dependency parser identifies potential aspects in textual data, and a pre-trained deep learning model extracts visual features from images. A sentiment analysis model predicts the sentiment scores of the textual data. These components are combined to form aspect-sentiment pairs. The second stage uses the proposed AoM model to classify the extracted aspect-sentiment pairs. The AoM model consists of a semantic graph convolutional network and a sentiment graph convolutional network. The semantic network captures semantic relationships between words in textual data, while the sentiment network focuses on sentiment relationships. By combining these networks, the model aggregates both semantic and sentiment information to improve accuracy. Experimental results on two datasets demonstrate the effectiveness of the proposed method, outperforming current state-of-the-art methods. However, the authors acknowledge limitations, including challenges in handling colloquial expressions and the need for external knowledge in predicting emotional sentiment related to current issues. Future research directions include addressing these challenges and exploring new solutions for dependency parsing and emotional prediction. Aspect-based sentiment analysis has emerged as a crucial area of research, particularly in the context of multimodal data. This paper presents a comprehensive overview of various methodologies and techniques employed in this field, emphasizing the importance of integrating visual and textual information to enhance the accuracy of sentiment analysis models. The authors discuss several key concepts, including cognitive brain models, graph convolutional networks, and region-aware alignment networks, which are designed to capture complex relationships between aspects and sentiments in multimodal data. They also emphasize the role of common-sense knowledge and effective information in improving the performance of these models. The paper provides an in-depth analysis of different approaches, such as the use of attention neural networks, dynamic and multi-channel graph convolutional networks, and position-aware tagging for aspect-sentiment triplet extraction. Moreover, it explores the application of vision-language pre-training for multimodal aspect-based sentiment analysis, demonstrating how this approach can significantly enhance model performance. The study addresses the challenges posed by errors in automatic speech recognition, (ASR), and proposes sentiment word-aware multimodal refinement as a potential solution. In addition to these advancements, the paper addresses the issue of named entity recognition in social media posts, suggesting the use of multimodal representation with embedded visual guiding objects. This approach leverages both textual and visual cues to improve entity recognition accuracy. The research concludes by emphasizing the importance of integrating cognitive, common sense, and effective knowledge into multimodal sentiment analysis models to achieve more accurate and comprehensive results. It also identifies potential avenues for future research, including the development of more sophisticated models capable of handling complex multimodal interactions and addressing the challenges posed by noisy or incomplete data. Aspect-based sentiment analysis and multimodal sentiment classification have witnessed significant advancements in recent years. A unified generative framework for aspect-based sentiment analysis, proposed by Hang Yan et al. In 2021, provides a foundation for subsequent research. This framework is built upon by Li Yang et al.'s 2022 cross-modal multitask transformer, which explores end-to-end multimodal aspect-based sentiment analysis. Jianfei Yu and Jing Yang's work on adapting BERT for target-oriented multimodal sentiment classification is also notable. Their entity-sensitive attention and fusion network for entity-level multimodal sentiment classification, proposed in 2019, demonstrates the importance of attention mechanisms in this domain. Furthermore, their research on improving multimodal named entity recognition via entity span detection with a unified multimodal transformer, published in 2020, highlights the potential of transformer-based architectures. Other key studies have contributed to the advancement of aspect-based sentiment analysis and related tasks. Yuan et al.'s 2020 Graph Attention Network with Memory Fusion for Aspect-Level Sentiment Analysis showcases the effectiveness of graph-based attention mechanisms. Zhang et al.'s 2018 Adaptive Coattention Network for Named Entity Recognition in Tweets demonstrates the importance of adaptive attention in multimodal sentiment analysis. Zhang et al.'s 2022 work on learning disentangled representations for multimodal cross-domain sentiment analysis highlights the potential of disentangled representations in this domain. Collectively, these studies establish the significance of multimodal fusion, attention mechanisms, and transformer-based architectures in aspect-based sentiment analysis and related tasks. By building upon these advancements, researchers can tackle the challenges of multimodal aspect-based sentiment analysis, ultimately driving progress in this field.